So I'll just discuss, I'll give an overview of the work that we've been doing on dynamics of water. I won't go into full details. I'll give the reference if anyone is interested. This work is published, so you can read up. I want to thank Dr. Mukherjee because he gave a very nice introduction to the reorientational dynamics of water, so it makes my life easy to talk about this. And so basically a very brief introduction for why this aspect of understanding dynamics of water is important. It is important because, for example, for proteins, which are usually found in salt solution, basically water, you have different kinds of dynamics that come into play depending on where the water is situated. So the water behavior, which is close to the macromolecule surface, is very different from a bulk water. A lot of aggregation happens in water. You have, for example, the entire cell membrane forms because you have hydrophobic interactions coming into play. You have mechanisms like what Dr. Maiti was talking about in terms of water permeation through very confined channels, in which, again, you have this reorientational kind of dynamics that happen. And it's important to understand what are the things that affect these kind of dynamics. So basically, I'm going to refer to this again, so I'll just give just one slide about how I'm going to view water in this talk. The water is going to be viewed as more of a fluctuating hydrogen bond network. So you can look at water as many different ways. And for the purpose of this talk and trying to understand the question that I'm going to ask, we're going to look at water as a fluctuating hydrogen bond network. The typical energy scales, the hydrogen bond is about 3 kcal per mole. So it's very easily, water can make and break these hydrogen bonds at room temperature. One of the properties that water always tries to achieve is to maximize the number of hydrogen bonds that it can form with its neighbors, which is theoretically 4, but typically at room temperature, it's about 3.5. So the question that I'm trying to ask here is, I know what happens, Dr. Mukherjee explained about this dynamical properties of how the water molecule reorients because of this formation and breaking of hydrogen bonds. And the typical time scale is few picoseconds. 2.6 or about 3 to 5 picoseconds is a typical time scale over which this reorientation of water molecule happens for it to change its partners from one to the other. So the question I'm trying to ask is, what happens to this reorientational correlation or the dynamics when I add salts in this? Now, one would think this is a very simple question and the answer should have been obvious, but it is not so. Just to get some understanding about these different terminology, there's something called a solvation shell, which is defined around an ion. So of course, I'm showing a very idealized case of a single ion in water. Of course, in general, you have many ions and you have these solvation shells which are merging between different ions. So I can think of there is an ion and I can define what I call these solvation shells. The definition of these solvation shells comes from experimental, and also you can do simulations where I try to understand what is the location of water molecules, which are the first location of water molecules or the first location of oxygen and second location. And you can see that typically the first solvation shell radius is about 2 to 3 angstroms, and the second solvation shell radius is about 4 angstrom. So I'm putting up this slide to give you an idea about the length scales we are talking. We are talking about length scales of 2 to 5. And when I use the phrase long ranged in my subsequent, I mean long range in terms of 5 to 6 angstrom. So this is different from the long range that probably it's not in terms of meters or whatever. Literally, we're talking about few angstroms. You can also see how many, there's a question of how many water molecules are there in a particular solvation shell. That depends on the ion. For example, if I take magnesium, which is highly charged, +2, highly charged, and polarized, you have about 6 water molecules. And of course, this number changes from ion to ion. This is a divalent ion. You have about 6 water molecules. And also this definition changes because for magnesium, the lifetime of water molecules in the first solvation shell is very large. So it becomes a bit difficult to say what this number would be for other ions, because the lifetime of water molecules in the first solvation shell will be very, very small as, let's say, for sodium or something of that sort. So typically, the reorientation time scale of a water molecule is 100 picoseconds. So if you remember, I said earlier for bulk water molecule, this water molecule reorients every 3 picoseconds. But if I look at water molecules in the first solvation shell, they are more or less rigid on that time scale, obviously. So they stay in that orientation for about 100 picoseconds. So you can see there are orders of magnitude of difference in this reorientation of water molecule that is happening. And so there's a phrase which is used, which is called slow waters. So this waters, the dynamics have been sort of retarded. Again, you can understand why this would be relevant in terms of implications of many things, because even if you talk in terms of this flow of water through nanochannels, if you have very slow waters, it can impact things like the viscosity, the dynamical properties, and you have many biological events that happen in this water. So the bigger question one can think of is this kind of retardation of these dynamics of water by the ions. What are the larger implications in this? What are the implications that come in terms of, let's say, even hydrophobic mechanisms? Are there any implications? Are there any waters that are found at what I said earlier, long range distances? So these are some experiments and simulations that are there in literature. There is a controversy on this as to whether, so the question that I'm asking is very specific. If I have an ion in water, how far do I find a slow water? Or how far will I start seeing bulk water again? Is it confined to first solvation shell, which I said is about 100 picoseconds is what happens? Or is it up to second solvation shell? How long do I actually see these effects that percolate from the presence of ions in this? So there are experiments that suggest that the effect of ions is largely confined to first solvation shell. Most of the simulations also say the same thing, that they are confined to the first solvation shell. There are new experiments. This is one of the experiments. In fact, if you see, this is the same people who have actually revised now, because now there are femtosecond spectroscopy experiments that are possible. People can probe the dynamics of this water at that level. And these experiments suggest that, in fact, if you take strong divalent ions like magnesium, it is possible that these effects are well beyond the first solvation shell. So that's what is seen in the experiments currently, but there's still some controversy. But the other question one can ask is, okay, this is experimental, but simulations, how come they have not shown this? If this is true, why is it that most of the simulations do not show any effects of presence of ions beyond first solvation? I think the answer most likely is rather simple, and it's in terms of nomenclature and definition of what is called the solvation shell, which I defined earlier. So as I said, this concept of defining the solvation shell in terms of spherical shells makes sense if I have one ion in water. Now that I feel it makes no sense if I have multiple ions, which is normally the case if I take even 0.15 molar concentration, which is a typical biological concentration, or even 1 molar or 2. This concept of spherical shell sort of breaks down because now I have intermixing of shells. So I can have an ion, I have first and second, I have a nearby ion which its second solvation shell is now mixed with the first solvation shell of another ion. So if I am trying to look at water molecules which are beyond the first solvation shell, and I know that they would be very small in number, when I average out these properties, I think I lose whatever is the small number. So the problem literally comes down to identifying those very few water molecules which are beyond the first solvation shell and whose properties are the ones that I should be looking at to answer the question whether there are any effects beyond the first solvation shell. So I think the problem in simulations is that what people do is still look at this definition of solvation shells in a spherical manner, and in fact they are missing out on all this very small percentage of waters. So as I said earlier, so I'm going to look at this problem as completely different. So we don't look at water now as in any terms of spherical shells. We don't invoke the concept of solvation shells. Rather, we look at the problem in a different way. I know, or I can think of water as a fluctuating hydrogen bond network. Now I add ions. These could be any kind of solutes. They could be hydrophobic or hydrophilic. In this particular case, they happen to be ions. Once I add ions, what I see is that this network, there are defects that are coming to pictures. So the same spanning sort of network, now when I add ions, you have these domains that are coming up, which are separated by these ions. And then we ask the question, what is the property of water molecules at the edge of these domains? So now imagine you have a network and it's broken up into domains because of the presence of these ions. And we ask the question, what happens to these ions which are at water molecules which are at the edge? And they are not, they're not happy molecules because tetrahedrality is not valid. They're not forming the number of 4 or 3.5 hydrogen bonds that they would like to form. So they are frustrated water molecules. And among this water molecules which have been affected because of presence of ions, we further ask a classification. Can I identify the water molecules which are beyond the first solvation shell of any ion? And we look at that subpopulation of water molecules and we look at their reorientational dynamics. And so this is the main result. So what we are looking at is we are looking at the dipole vector of a water molecule. And these are the water molecules which are beyond the first solvation shell. And this is, the black line is for the pure water, where you can see that once as a concentration dependent for magnesium, if I look at the water molecules beyond first solvation shell, there are a lot of slow waters that are coming. So the dynamics is retarded for molecules even beyond first solvation shell. So the summary is that this supports the latest experiments that there are water molecules that are found beyond. In fact, we find, I have no results, but they are in the paper. We find that these can be found as much as 6 angstroms away from the ions. And the numbers are very, very small. So you can see for 2 molar, there are about just 6% of these water molecules. If I'm looking at, let's say, 5,000 or something, it's a very small fraction of the water molecules which are affected. And most likely, the other simulation results miss out precisely because of how they are looking at the definition of these ones. And you can have a lot of results and more discussion in the paper. Any questions?
Thanks.
So the effect of solute, or some putting in some molecule, that depends on the size. That's pretty well known.
Of course.
Thing in, so is it consistent? I mean, what you're saying is consistent with this kind of, like, for small solute,
Yes.
the hydrogen network is hardly affected. So basically, it's like, the solute goes inside the cavity of water molecules without affecting the hydrogen bond network.
So okay, so this is specifically for ions. For solutes, like if I look at hydrophobic small solutes that would be dissolved, I think in general it's a difficult problem because to achieve some sort of aggregation or something, I think the timescales involved to see an equilibrium state in which I have hydrophobic solutes in water, I think it's harder. But maybe this happens, but I cannot answer anything because I have not done that.
Vani, I guess, I mean, what you said in the conclusion slide was that you could find evidence for perturbation in the second solvation.
Yes, yes.
But in principle, the manner in which this decays is more important. If you look at,
so I have not shown the data. So we have fit these things to multi-exponential fit because, as again Dr. Mukherjee said, there are many time scales here. So we fit it to a multi-exponential. And we do see that the order of magnitude, there is a difference in terms of slowing down. So we fit the results to tri-exponential ones. So we see that there is order of magnitude difference. So I didn't go through that, but yes, we do.
Time scales for.
So we try, at least in the paper, we try not to assign a particular physical process to that because we were not sure. But a couple of things are along the lines of you have this jump mechanism. So what we feel is that you have now these domains. So it's what's happening, I think, is there's a coarse graining that's happening. So you have the first two probably correspond to intra-domain, where the water molecule probably is, looking at what is happening. But I think the third one is coming because, as I said, when you have these domains, you have now a domain and domain interacting. So if a water molecule which is sitting at the edge, if it wants to change its direction, it can't do so easily unless the entire domain changes something, because that's the slowest. So what we feel is that as you put these ions and these domains come up, you have a coarse graining of the system happening, and now you require the entire domain to, and that's probably is what is contributing to the third one, which is the longest time. That's what we feel. No, MgSO4. But you need a polarizable model for that, and we didn't want to go into that. So, yes, we did. Yes, so for cesium, actually, we see that they have no effect. It's same with that. It's consistent with Hofmeister series. That for cesium, we do not see anything, but for magnesium, we see this effect. So this depends on the valency. Yeah. For water, we had tip 4p, and magnesium was, the parameters were used, which were consistently derived for tip 4p water. No, I understand that force field can be. Particularly for magnesium. I just want to, if one just last question is, after our paper, actually, there was another paper by Lipowski where they use polarizable model and they get similar results. So.
Okay, thank you, Vani. Let's